Hello everyone, how are you? I hope all of you guys are doing good and the semester is going very productive for all of you. Okay, so welcome to the second portion of the course. We are going to focus on transistors in this part of the course. Mainly, we will cover contents from three chapters. Chapter number 5, which is MOSFETs. Chapter number 6, which is BJTs, another type of a transistor, and chapter number 7, which is transistor amplifiers. So we will mainly cover the contents from these three chapters. Okay, so let's start with chapter number 5. In this chapter, we're gonna mostly talk about one type of a transistor, which is metal oxide semiconductor field effect transistors, MOSFETs. Very important. Out of the two, MOSFETs are more commonly used in recent days. So more MOSFETs, very important chapter. And another important thing related to the chapter is we are going to cover the basic structure of how MOSFETs which components MOSFET has, the physical structure of the MOSFET. We are also going to talk about how we can operate these transistors in different modes, how we can operate that as an amplifier, as a switch. We will also talk about certain DC applications of MOSFETs. We will cover also some of the MOS amplifiers topic from the chapter number 7 right after chapter number 6. And once the MOS topic is complete, MOSFETs topic is complete from chapter 5 and chapter 7, then we will move to the BJTs chapter number 6. So we will cover topics from the chapter number 6, and we will come back to chapter number 7 for the BJT related topics. Okay, so with that, let's start with this chapter number 5, metal oxide semiconductor field effect transistors. Don't worry about the name. Very shortly, this name will be more clear to you on where all of these words are coming from. Okay, I'm going to give you, in this lecture, we're going to talk about, very briefly, we're going to discuss what the transistors are. We're going to talk about the physical structure of a MOSFET. And we will start talking about the operation of the MOSFET as well. And over the next few more lectures, we're going to continuously talk about the operation of the MOSFET in very, very detail. But we're going to start that today. Okay, so transistor. Transistor is a 3-terminal semiconductor device as compared to a 2-terminal semiconductor device, which is a diode. You guys have studied the diodes earlier in the course, right? It's a p-n junction, 2 terminals. Transistor is a 3-terminal device. Transistors are very commonly used it's kind of a very important part of our lives now. Transistors are there in almost many electronic devices. We can build microprocessor, memory units, logic units, amplifiers, a bunch of these things using transistors. There are billions and billions of these transistors packed on a very small microprocessor, right? Those microprocessors are there in your laptops, in your computers, in your smartphones, smartwatches. So this is very important. So I really hope that you guys will put a good amount of effort in understanding and learning these transistor operations, especially if you want to work at Intel or some other semiconductor industries. There's a huge semiconductor industry, and transistor is an important component. Okay. So let's move forward. Okay, so if somebody will ask you, what is a transistor? And if you have to explain that to a non-expert, very simply put, transistor is a 3-terminal device in which if we can change the input signal or the voltage in between the 2 terminals, we can control the current or the signal flowing in the 3rd terminal. So therefore, we can use it as a switch, as a logical inverter, So this is, yeah, this is probably the most simplest definition of a transistor for a non-expert. This omits a lot of details and a lot of technical details. We're gonna cover that. We are going to talk about in this rest of the portion of the course about two semiconductor transistors. One is MOSFETs, metal oxide semiconductor field effect transistor. This is chapter number 5. We are also going to talk about bipolar junction transistor, which is chapter number 6. Okay. So moving forward, MOSFETs. MOSFETs are more commonly used in making electronic devices as compared to BJTs, especially microprocessors and memory units. There are several advantages comparatively to BJTs. And over the course of these lectures, subsequent lectures, these things will be more clear to you as well on why MOSFETs are better than BJTs, or in certain respects they are better, in certain respects BJTs are better, or in certain applications, if you will. Okay, so MOSFETs. MOSFETs are can be made more smaller in dimension, so we can pack more and more transistors on a smaller surface, right, on the same surface area. So this means that we want, in microprocessor, we want to put more and more and more and more transistors there, right, to increase our processing speeds. So that is helpful. Manufacturing process of these MOSFETs is relatively simple. Again, it's complicated, but it is relatively simple compared to the BJTs. And MOSFETs also require very small power to operate, which is kind of a very important component, right? We want our batteries in all of our electronic devices, all of these devices, smartphones, laptops, to just run forever. Ideally, yeah, but for a longer time. So yeah, we want all of these electronic components to use as much power as possible. So this is an important consideration to make. Here's just an example that, for example, scientists have packed more than billions, like 4 billion transistors on a single IC chip. IC is integrated circuit, if you don't know. And when we pack a lot of these ICs on a single chip, we like to call this as VLSI, digital circuits, which means very large scale integrated circuits. And we develop them for microprocessors, memory units. We can also build our regular electronic devices as well using transistors. For example, filters for noise filtering, for example, amplifiers. Using this MOS technology, using both BJTs and MOSFETs, we can do that. Of course, we don't need millions and billions of transistors in making the amplifiers and the filters. Another important thing is we can also do something that is called as a mixed signal design. Which essentially is that on a same integrated circuit, we can have analog and digital operations done by using these MOS transistors, this is known as a mixed signal design. We will not talk the details of this mixed signal. We will not cover the mixed signal circuits and or the design for this specifically. So this is just for you guys to know. Okay, so in this chapter, we talked about this. We are going to cover the physical structure of the MOSFETs, its operation, the terminal characteristics, and the DC circuit applications. And especially if you guys are interested in how you can use these transistors and develop logic gates, basic microprocessing units, memory units, I would advise and highly recommend taking the next course on digital electronics. Okay, so let's move to the now we're going to talk about the basic structure and the physical operation. Okay, so before I will show you the physical structure of the MOSFET, there is another term that you're going to come across during these lectures. That is something that is called as an enhancement type. Very briefly and simply here, and you will understand it much more clearly during the next lectures. There are two types of MOSFETs. One is called as an enhancement type MOSFET. Another one is called as a depletion type MOSFET. Essentially, in an enhancement type MOSFET, as you apply a voltage signal to one of the terminals, or once the electric field is applied, the conductivity increases, right? So the conductivity is enhanced. So that is why it's called an enhancement type MOSFET. For now, don't worry about the depletion type or the enhancement type names. This will become much more clear in the next lectures. Okay, so let's talk about the physical structure of a MOSFET, right? So we have two types of MOSFETs again. One is whether it's a depletion type or enhancement type. One is the NMOS and one is a PMOS. We will talk about the specific differences shortly about in between these two types. So let's start with the NMOS. So this is a structure of an NMOS. Now, let's look at this structure now. We have terminals. This is our source terminal. This is our gate terminal. This is our drain terminal. And this is our body terminal. So if you remember the last slide, I mentioned that the transistor is a 3-terminal device. So why do we have 4 terminals here? Right, okay. So the most important terminals for this devices, for these transistors are, again, these 3 in terms of a MOSFET: source, gate, and drain. Body terminal is also used in certain applications and to achieve certain operations. Another important thing is, for example, how yeah, so let me get back to the body terminal in a minute. Okay, let's look at the structure in a slightly more detail, and I will get back to the body terminal, or what's the use of a body terminal at all here. Okay, so over here we had these terminals: source, gate, and drain, and body. And simply during the next slides and more importantly, even for the next subsequent lectures, even the exercise problems, whenever you're going to come across the circuits and or the device images, you will never see these complete words: source, gate, and drain. They are usually written by their symbols. D is for drain, G is for gate, S is for source. Okay, now so let's look over here. So we have our source region is N-type material. Our drain is N-type material, and then we have this body where we have made these source and drain. This is a P-type body. Now, if you remember from the diodes lecture earlier, that N-type material is an extrinsic semiconductor in which, for example, the silicon crystal lattice, it is doped with pentavalent impurities, and we have a large amount of electrons as majority charge carriers. And in a p-type material, it's again an extrinsic semiconductor in which we dope with the trivalent impurities, so we have a large amount of holes as majority charge carriers. Okay, what else is here? Over here on this in this transistor, we have this region. This is called as a channel region. I will just for now just let's say that this is something that is called as a channel region. And why this is called a channel? Because it will provide a channel for the current to flow in between these two terminals. So in between source and the drain, the current is going to flow, and we are going to talk about how it flows, and we are going to discuss channel a lot more in detail shortly. But for now, this region is called as a channel. Okay, what else is here? We have these regions. These are metal contact pads or metal electrodes. So we make these metal electrodes to the body, to the source, to the drain, and to the gate, right? So this is to the creating these metal terminals or electrode terminals to provide the input signal and getting the output signal. Now we have this dashed or shaded region. This is an oxide layer, a very small oxide layer, and the thickness of this oxide layer is 1 to 10 nanometers. And we will soon realize later part of this lecture and the next lecture that this is going to serve as a dielectric, and essentially we are going to end up making a capacitor in this region. Anyways, we will discuss that thing as well in detail. Okay, so for now, another important thing, for example, this L, this is the length of this channel in between source and drain. Another dimension is the width, which is in between, which is the width of the oxide layer, if you will, or width of the or the electrode terminals. Okay, so coming back to the body. Now what will happen is we will discuss in more detail again, but briefly speaking here, we normally just in order to operate the transistors for different applications or for certain regions, we're going to talk more in more detail. We just require source, gate, and the drain terminal. And what usually happens is the body terminal is normally connected to the source terminal and or is grounded and or is connected to the negative supply in case of an NMOS to create a reverse bias condition or normally off condition for the transistor. What I just said about the body terminal, this will become much more clear again shortly. Okay, so let's continue with the structure. Some of the things that I've just said. We have a substrate and or the body terminal. Again, this is a substrate and or the body. It is a p-type, a lot of holes. It also provides a physical support of the device, right? So what does this mean, providing a physical support of a device? For example, your device, this is just one transistor, right? The device can be a pretty big device. Let's suppose, yeah, this is a big region in which we can have multiple transistors. It houses 3 transistors, for example, over here, right? With a common body or a common substrate. So what usually happens is, and this is probably coming back to the body again, that we can connect the body of this entire substrate to a specific voltage to create a normally off condition. Normally, to induce a cutoff condition for the transistors. Now, so that is why this body, another important thing is this body, which can house in an integrated circuit. The body can be pretty big, and we can have millions and more billions of these transistors in certain in the same integrated circuits. So that body and substrate also provides the physical support. Okay, another important thing is over here is this N plus, right? So we said this is something that is called as N plus. Whenever you see a plus over here on the top of N over here, this means heavy doping, right? So this is N, and whenever you see a negative sign, this means light doping. Okay, so both source and the drain over here are heavily doped, right? And again, the doping is to create an N-type material is to putting out the pentavalent impurities in an intrinsic semiconductor. And that will result into a lot of these electrons as a majority charge carriers. Okay, so N positive as heavy doping and negative as light doping. Similarly, we can also make a complementary thing. P positive heavy doping for the P type, P negative is light doping for the P type. Okay, why do we need heavy doping? We will come back to this thing shortly. And that's a kind of a good conceptual question, important question that might come in exam. Okay. Okay, we talked about this. Again, we talked about this, that this is the silicon dioxide layer, this layer. Right, this is a silicon dioxide layer, and it is very, very small, 1 to 2 nanometers. And this is going to serve as the dielectric for the capacitor we're going to discuss shortly. Okay. And then we talked about this thing as well, that we essentially deposit the metal to create the electrodes or the contact pads for the, kind of contact pads for all the terminals of the device. We have this is that metal deposited, metal deposited, metal deposited, and metal deposited to create these electrodes. Okay, so we ended up getting 4 terminals, gate, source, drain, and the substrate of a body. Okay, so by now you will have realized where the name of this MOSFET is coming from, right? So MOSFET, MOS, metal oxide, we have an oxide layer, semiconductors, we have semiconductor materials here, N-type, P-types, and then we have something that is called as field effect transistors. We're going to come back to this term again and again multiple times, and over the time this will become more clear. But essentially, field effect transistor means that you will realize that when we are going to talk about the operation of this transistor, we said that this is gonna behave like a capacitor. This gate and the dielectric region is going to behave like a capacitor. So we are going to induce an electric field, and that electric field will will help conduct the channel. And so that is why it is called as a field effect transistor. We're gonna come back to this point again and explain more. Okay. Okay, in some just kind of another small thing. In some literature, MOSFETs are also referred to as insulated gate field effect transistors, or IGFET. Why they are called like that? Because your gate electrode is insulated, right? Over here, this is your gate electrode. Your gate electrode is insulated from the entire body of the transistor from this oxide layer, right? So that is why it is called as an insulated gate field effect transistors as well. Okay, so now if you will have realized now that in this transistor we have again sources. We are just talking about the NMOS. We're gonna come back to the PMOS again. For an NMOS, we have our source is N-type, our drain is N-type, and our body or a substrate is P-type. So we essentially have two different, we essentially have two PN junction. This is NN, this is a P, and this is an N. So we have a PN junction, a PN junction. So we have two PN junctions. And in normally, so what happens in a normal off condition, if we will connect, the body is usually connected to the source. And then what we do is in the normal operation, our drain is usually at a higher potential as compared to the source. And if our drain is at a higher potential as compared to the source, and you will connect the body to the source as well, that will make sure that both of these PN junctions, the PN junction of the gate and the source, and the PN junction of the drain and the gate, are both reverse biased and cut off. So that is another, this is a kind of another important concept over here, because it helps us to create the reverse bias conditions in an off condition, right? Reverse bias condition for the both PN junction, and this is important, right? For example, if in a bigger substrate, if we have multiple transistors that are operating at different voltages, we may wanna, rather than connecting a body just to a ground, we may wanna connect a body to a negative power or a negative voltage supply that is the highest or the least highest negative, just to make sure that all the transistors in this entire body are reverse biased. Okay, this concept again, this concept of the body connecting the body to the most negative supply will become more clear. We're gonna have a dedicated, not the entire dedicated lecture, but a portion of the lecture talking about this concept as well in more detail. For now, just remember that for simplicity, the body is connected to the source, drain is usually at a higher potential, and that will make both of these PN junctions reverse biased. Okay. And that will also help in making sure that the body and the substrate will not have any effect on the operation of the device. Okay. So we're going to talk about the operation of a device, right? So how we can operate a device. In order to operate a device, what we usually do is we apply a signal to the gate terminal. This will help the current flow in the channel, right? But how will this entire thing happens? This is what we're going to talk about, right? Okay. So let's just consider a condition in which we apply a zero voltage to the gate voltage. And I think this is a kind of a condition that we just talked about, but I'm kind of writing this thing again. And the thing you may notice that in my lectures that there's a lot of things that I'm saying, and most of these things are also written up in the text in the slide, so that I hope that this will be helpful for you. Okay, so what happens if we apply a zero terminal to the zero voltage to the gate terminal? Again, if we apply a zero voltage, if we will just ground this thing as well, we have two PN junctions, right? This is what we just talked about, that we have two back-to-back diodes. We have a PN junction between drain and the gate, drain and the body. And then we have another PN junction between the body and the source. We already talked about this thing, right? And this will make sure, so if we have these two p-n junctions and the gate is at the 0 voltage, this will make the junctions reverse bias and no current will flow. So this is kind of a off condition. In that condition, the path over here, this channel region that I'm talking about, it has a very high resistance, right? So we will realize, I'm going to talk about in more detail why this is called as a channel, because this is going to be, this is a region where the current is going to flow. And in a normally, again, in an off condition, when the drain is at a higher potential than the source, but the gate is off, but the gate is grounded, nothing is going to flow in this channel region, and our transistor will be off because both of these, because both of the p-n junctions are reverse biased or off. Okay, and the resistance of that channel is extremely high. Okay, now so let's start talking about now how the current flow actually happens, right? Okay, so consider the following situation. Okay, so this is the same transistor. We have connected the body to the body terminal to the substrate. For simplicity, until I will specifically talk about the topic of a body, for simplicity, even in the questions and in the lectures, you can assume that the body is connected to the source and is grounded. Okay, unless specifically stated otherwise. Okay, so coming back to this is again the physical structure of a NMOS transistor. In this NMOS transistor, the body is grounded, the source is grounded, the drain is grounded, and we apply a gate to source voltage here, to the gate terminal, right? Okay, so and this is the metal electrode. So what will happen? We know that this is an N-type source, N-type drain. N-type source and N-type drain are going to have a lot of these majority electrons, right? And a P-type substrate over here is going to have a lot of these holes here. In this entire body, it's going to have a lot of these holes. So what will happen? So as soon as I will apply this gate to source voltage to the gate terminal, a positive voltage will appear over here. So what this positive voltage will do, this will repel all of these holes downward. Now these holes will be repelled downward and a depletion region will be created. So one thing is holes repelled, wrong spellings, downward, depletion region. Second, so what happens second, right? So the holes will be pushed downward. Now again, this is the gate electrode is at a positive potential, so this is going to attract these electrons over here in this region, right? So this region is going to be filled with electrons, right? Electrons will go to the channel region, right? We discussed that this entire region is a channel region. So the electrons from the source and the drain, where they were majority charge carriers, will be attracted to the channel region. So these two things happen. And so once we will have sufficient number of electrons in the channel region, this phenomenon is called as inducing a channel, right? Or creating a channel or inducing a channel. So once, and now another important thing that you may have realized by now is in a P-type substrate, you ended up creating an N-type channel, right? So this is an NMOS. In an NMOS, your body is P-type, your channel is N-channel. So that is why it is called as an NMOS. The things are exactly opposite in a PMOS. In a PMOS, your source and drain are P-type. The body is N-type. And the channel will be opposite to the body. So the channel will be a P-type. So that is why the other one is going to be called as a PMOS. We are going to discuss a PMOS later. Right now we are going to focus on one and transistor, NMOS, and we will realize that the PMOS will essentially be mostly just flipping the batteries, or flipping all of these voltages. We're gonna come back very shortly. In the next couple of lectures, we're gonna come to the PMOS too, probably the next one. Okay, so by now we ended up inducing a channel. We ended up applying a gate voltage. The positive voltage appears at the gate electrode. This ended up pushing all the majority holes downward, creating the depletion region. The electrons in the source and the drain ended up attracting in the channel region, and we ended up creating a channel. So this is an N channel that we ended up creating. Okay, what's the second thing that will happen? Or the third thing now. So what will happen after this thing? And I think that will be a topic of our next lecture. We're going to discuss in much more detail, but I can give you a quick hint that what we will do is we will apply a small voltage, VDS. We will apply a small voltage here at the drain. So the drain will become at a higher potential as compared to a source. So when this will happen, right? So a positive voltage also appears here. What this will do is this is going to attract all of these electrons now, right? So your electrons will start to follow here. So your electrons will start to follow from the source to the channel to the drain terminal. However, conventionally, we know that the flow of the current is opposite to the flow of electrons. So our current will start to flow, which is called as a drain current. So the drain current will flow from the drain to the source. Okay, so this is the very basic how this entire operation happens. I ended up writing most of these things, so we will very quickly go through it. Right, so the source and we are grounded the source. We ended up grounding the source and the drain. Then as we apply a small gate to source voltage, the positive charge appears on the gate electrode, and the free holes will be repelled right downwards. This is what we are talking about here. And as they leave downward, we ended up creating a depletion region here. So the next thing is, so once the depletion region is created, the second step is that the electrons from the source and the drain are attracted towards the channel region, right? So the electrons from the source and the drain ended up being in the channel region. So that is why it is called as an N channel. We talked about this. Now, if we apply our drain to source voltage, right, this is when I just talked about when we apply our drain to source voltage, all of these electrons will start to flow from the channel and the drain into the drain terminal. Conventionally, our drain current will be from the drain to the source, opposite to the flow of electrons. Okay, so we ended up inducing an N channel here in an NMOS. So okay, yeah, so another important kind of in terms of naming conventions, this layer, this channel is also known as this channel, right? So this channel is also known as an inversion layer. Why they are called an inversion layer? We just talked about this, right? In an NMOS for a P-type substrate, we ended up inverting. Our channel is an inverse of that type. Our channel is an NMOS. In an NMOS for a P-type substrate, our channel is N-type or N-channel. In a PMOS where substrate is N-type, we ended up creating a P-channel, right? So that is why it is called as an inversion layer. Okay. So one more brief concept before we wrap up this introduction lecture, and that concept has to do with the threshold voltage. In order to induce a channel here, right? In order to make this entire operation happen, and in order to induce a channel for the current to flow, the most important component is the amount of this voltage, right? So there exists a threshold voltage that if your gate to source voltage is less than the threshold voltage, channel will not be induced. So our gate to source voltage must be greater than the threshold voltage for the channel to induce, right? Okay. And this threshold voltage, it depends again on a bunch of factors, on a bunch of transistor fabrication processes, but normally it is anywhere from 0.3 to 1 volts. So our gate voltage that we apply to the gate terminal, this thing should be greater than that specific voltage, 0.3 to 1 volts or threshold voltage. Then the channel will induce, otherwise not. Okay, so with this we are going to this is what we just talked about. In order to make sure that we are going to have a conducting channel, our gate to source voltage should be greater than the threshold voltage, and it is usually 0.3 to 1 volts. Okay, so with that we are going to wrap up this lecture, and in the next lecture we are going to talk about in much more detail about the operation. We will also discuss about how this entire capacitor is formed. Right, so this is a capacitor. We have on the top electrode, we have a positive layer, positive charge. On the channel, we have a negative charge, and in the middle, there's an oxide layer, which is a dielectric, right? So we ended up making a capacitor here. And we will also see different relations on the conductivity of this channel, right? And the electric field that can be applied over here. So why this is called as a field effect transistor. So that these are the topics for the next lecture. Thank you so much. I will talk to you in the next lecture. Thank you. Bye-bye.